All right, in this session we're going to be looking at stability, and we'll find that stability is exceptionally important in control systems because if they're not stable, then the system really can't be used. All right, so there are three requirements in designing control systems. We need to be conscious and keep track of the transient response, the steady state errors. If you remember, the steady state errors are things that are variations from the preferred particular response that you want, and stability. Now, stability in lots of ways is the most important aspect, because if a system is unstable, then really you can't control it. So the transient response and steady state errors are moot points. It doesn't really matter how far you're off the particular desired response. You can't design with it, and the system can be damaged or cause damage to itself, to others, and also to maybe the process that it is controlling as well. So by definition, the total response as always is equal to the forced response plus the natural response. And then the forced response is dependent upon the type and size of the excitation and on the type of system. And the natural response depends solely upon the system for its form, although the stored energy which provides the necessary stimulus will influence the size of the response. So defining stability using the natural response. If a system is stable, then you can see that Cn of t tends towards 0 as the time goes on. So as you get closer and closer to infinity, or as this time goes on, your operating system. The system will become unstable if it tends to infinity as time goes on, and marginally stable if that particular function neither decays nor grows but remains constant or oscillates. So basically nothing happens. Likewise, the total response, what we call the bounded input, bounded output, a system is stable if every bounded input yields a bounded output. So in other words, it's under control. It's unstable if any bounded input yields an unbounded output. It just goes haywire. So the stability of a linear system is a system's property and is dependent upon the external inputs, subject only to the condition that they are bounded in magnitude. In other words, they remain within appropriate limits. They just don't keep growing and getting larger and larger. Thus, it's important to see what property of the system controls stability. So determining stability using the natural response definition of stability in poles, a stable system is a closed loop transfer function with the poles only in the left half plane. That is, the poles in the left half plane and have negative real parts. An unstable system, closed loop transfer function with at least one pole only in the right half plane and or poles of multiplicity greater than 1 on the imaginary axis. That is, the poles in the right half plane and have positive real parts. Marginally stable, the closed loop transfer function with only imaginary axis poles of multiplicity greater than 1, and they are on the imaginary axis. So no, if the closed loop transfer function has only left half plane poles, then the factors of the transfer function denominator, that s plus qi, where qi is the real and positive or complex with a positive real root, the product of such terms is a polynomial with positive coefficients, and no term of the polynomial can be missing. If the term is missing, it implies cancellation. So that's not very good. Sufficient condition for instability or something being unstable is that all signs of the coefficients of the denominator of the closed loop transfer function are not the same. And if the powers of S are missing, the system is either unstable or at best marginally stable. But if all coefficients of the denominator are positive and not missing, we do not have definitive information about the system's pole locations. So as I mentioned about beforehand, when we talk about the mathematical background, bear with it if you kind of feel like there's a big gobbledygook. It's really the application of mathematics. So one way, there are a number of ways to go about determining or checking on stability. The Roth-Hurwitz criteria is the one that's going to be used in this particular introductory unit. So the RH, is another way to describe it. The Roth-Hurwitz criterion yields stability without needing to solve the closed loop transfer poles. It yields how many poles, but not where they're located in the left half plane or the right half plane or on any imaginary axis. So you have to start off by generating a Roth table. Then you interpret the Roth table to give the number of poles in the left half plane, the right half plane, or on the imaginary axis. Now, the importance or effectiveness of the technique is that it provides a simple yes or no answer to whether the system is stable or not. That's all it does. Useful, but that's really all it does. A bit of work to do it sometimes, but that's basically what it does. So generating a Roth table. Determine the closed loop transfer function is the first thing to do. Then investigate the denominator of the transfer function. Write the polynomial in decreasing order of powers of S. All coefficients need to be included. by 0 if absent. So if you've got an S squared or something, and it's 0, you write down 0 S squared. A useful preliminary step, but not essential. Can you reduce the sub, which can obviously cut down the amount of work you're going to do, is to divide the denominator by the coefficient of the highest power. For convenience, you can multiply by positive constants without changing the values of the rows. This is all the background stuff. Consider the nth order polynomial having n plus 1 coefficients. So P of S equals, as you can see, you've got all your coefficients. As you can see, they're decreasing as you go along, and also the powers of the S are decreasing. So your typical polynomial form. But write it in decreasing order of the powers of your particular variable. So it's S in this case. For an nth order system, the table will have n plus 1 rows. Now consider the first 2 rows. These are the actual coefficients of the polynomial. So you'll see, so S to the n. So what you do is you go and pick up that coefficient. You go to the second one, so every second one, n minus 2. Next one would be n minus 4, all the way up to until you get to the n, which is those last two, A2 and A0. Then for the S minus 1, you do this for each one. You keep going down, and you'll see, again, as I said, there's a mathematical background, but once we look at the example, it'll make more sense, hopefully. So you start with the coefficients, the highest power, and then take every alternative coefficient until there are no more. And then with the other one, start with the coefficient, the second highest power, and use the alternative coefficients until all have been used up. Okay, now for subsequent rows, each element is compiled using the 2 preceding rows. Each element in a new row is a fraction, and in any one way, all fractions have the same denominator. The denominator is equivalent to the pivot term, and will become obvious in a moment, which is the first element of the row immediately above. The numerator of each term are calculated apart from the sign, analogous to a denominator of a 2 by 2, as you can see here. Each matrix has a first column equal to column elements taken from the 2 preceding rows. The other column of the matrix is taken from excessive columns of the same row. So, yeah, okay, that's what it looks like. As I say, once we look at the example, it'll make more sense. Proceed in the same manner for all the other rows, so n minus 3, n minus 1, n minus 2, and basically follows. Just keep following this process, and you'll find that we generate the Roth table. Now, interpreting the Roth table, the number of roots of the polynomial, the denominator of the transfer function, that are in the right half plane is equal to the number of sign changes in the first column. Now, if the closed loop transfer function has all the poles on the left half plane, the system is stable. That is, the system is stable if there is no sign changes in the first column of the Roth table. As I say, let's try an example. Consider the transfer function. Now, again, when you look at the transfer function, you're only interested in the characteristic equation, which is the denominator of your transfer function. So P of S, the polynomial, is equal to, in this case, S cubed plus 5S squared plus 3S plus 2. So as we said, you write down your highest S power, which is a 3. You take the coefficient as 1. As we said beforehand, if that was 3, for argument's sake, you could divide through the whole thing and then start, but look, it doesn't really matter. It will work out either way. That was one of the suggestions given in the little rules above. So that's going to be a 1, and then you take every alternative term. So you go to the next one, which is 3, and the next term, it's 0, till you run out of terms. Then you go to the next power, which is S squared, and you're going to start with the 5, and then you take the next alternative, which is 2, and then you take the next alternative, well, there isn't any, so it's 0. So straight away, we've got 2 rows. So how do you generate? So we've got S3 row, and we've got the S2 row. How do you calculate the S1 and S0 rows? So that's what we're talking about with this little rule. So as you can see here, once you get these written down, you generate the rest of the table by using that little determinant kind of rule. So here we have, as you can see, 3 times 5 minus 1 times 2 divided by the pivot point. So that gives you 2.6. Let's move that up a little bit. So there's my 2.6 value. Let's roll that around. 2.6 value. Likewise here with the next one, you can see that we've got 5 times 0 and 1 times 0 divided by 5. See how we've now moved into this particular column. So that's why we're doing it that way. And then you end up with 0. So therefore now your next row, and then anything else left here, you just put a 0, just to keep the form of the particular Roth table. So now we've been able to generate the first 3 rows, and we need to find the 4th row, which is S0. So then as we move down, we're going to have concentrating on these two rows now to generate S0. So as you can see, that will be 2.6 times 2 minus 5 times 0 divided by our pivot point, which is 2.6. And then likewise, to find this next term over here in our particular S0 row, it's going to be 2.6 multiplied by 0 minus 5 times 0 divided by a pivot point, 2.6. So now we've been able to generate our Roth table, and there it is. So quite interestingly, if you consider the first column, there are no sign changes as you proceed from one row to the next. So if you look there, so we'll generate the whole table as we mentioned, and then if you look down the column, that's the most important thing. It's going to tell us all the information. See how that's a positive, that's a positive, that's a positive, that's a positive. Fantastic. So there are no sign changes as you proceed from one row to the next row. Thus, there are no roots with positive real parts, so therefore the system is stable. Okay, so it's as easy as that. Again, just a little bit of algebra, a bit of mucking around, but make sure you keep the form of this correctly and everything will drop out quite nicely. There are a couple of difficulties that can arise, and there are strategies for navigating that. So what happens if you end up with a 0 in that particular position that you're using as a pivot point? Now, since the pivot point or pivot term is the denominator of the next row, as you can imagine, you divide by 0, everything becomes infinite. So you can overcome by replacing the 0 pivot with an algebraic symbol. Just use epsilon for argument's sake, and then proceed as if nothing is amiss. Now, once the table is generated, determining if there are any sign changes, you can do that by evaluating any term containing that sigma value as the limit approaches 0, taken from both sides. So in other words, taken from the high level or the low level. What happens if all your row, all the values in your row is 0, so that occurs if the polynomial has equal and opposite roots, then the all row, 0 row will have an odd number label like S1, S3, or S5. Replace the all 0 row by elements that are obtained by differentiating the even order polynomial, which has coefficients taken from the row immediately above. These correspond to coefficients of an odd-powered polynomial. So once the Roth table is generated, you determine if there is any changes in sign anyway. And the over-existence of all row highlights an even polynomial, and an even polynomial whose roots are symmetrical at the origin is what's occurring. So therefore, there are imaginary roots. The two key problems that you'll encounter. And as I say, look, it looks like difficulty and it looks like it's quite complicated. But as you cycle through, if you do bump into that kind of example, we can talk more about it. But the reality is that it's solvable. And you can work around those types of issues. Now, stability in state space. The values of the system's poles are equal to the eigenvalues. And again, this is more mathematical background, but this is the key fundamental underlying principles that are involved. So those system poles are the eigenvalues of the system matrix A. The eigenvalues of the matrix A are the solutions of that particular equation. So if you're taking the determinant of S multiplied by the identity matrix for that particular size matrix. So if it's a 2 by 2, then it'd be the identity matrix for a 2 by 2. 3 by 3 would be identity matrix for a 3 by 3. Minus our matrix A would equal 0, which also yields the poles of the transfer function. Indeed, this equation is the characteristic equation for the system from which the system poles can be determined. I'm just doing it in a matrix form, looking at the state space. Thus, we can explore the stability of system represented in state space by determining the eigenvalues of the system matrix A and find their location on the S-plane. So here we have a system defined in matrix form, like we would think about when we're doing state space. So x dot equals that, x plus that times the control GU. So that's our input state function, and also there's our output y equals 1, 0, 0, x. Now, how many poles are in the left half plane, in the right half plane, and or on the imaginary axis? So all you got to do is go through and determine that particular expression and equate it to 0. And as I say, do it in bite sizes, do it bit by bit. So there we are, we're dealing with 3 by 3. So the identity matrix for a 3 by 3 multiplied by S will give us S 0, 0, 0, S 0, 0, 0, S. Minus our original A, there's our A matrix. So we end up with this, find the determinant of that. So again, you've got to go through and again, keep your wits about you, make sure you write down all the brackets, except important to include the brackets. And then you'll find that we end up with this cubic expression here. So therefore then, that's our characteristic equation. What we're going to do pretty much is, like we did beforehand using the Roth-Hurwitz process, go through and generate your table. So if you remember, we write down S3, S2, S1, S0. With S3, you take your first coefficient, which is a 1. we take the alternative term, which is the -7, write its coefficient down. Then we're generating the S squared. We're obviously starting with -6 as the coefficient, and then we take the alternative, which is -52. And you can put a 0 here and a 0 there if you want to, just to continue the form, because when you do some calculations, that will become important. So what we're going to do is generate the S1, and if you remember, we're going to do like a determinant. So it'll be -3 times -7 minus 1 times -26, and that's our pivot point. Get a value. There's a 0 over here. So pretty much we can find our values for this particular row S1. So when we go through and continue doing our calculations, we'll see that that will be -26. And then when we get a factor like this, we can, just multiply through and get rid of that particular, term, because you can leave it there. You can work with it. It just means it's going to make a fraction, I suppose. So if you divide through by that, then you'll end up with a nice number of -1. And then obviously you just follow through your process and calculate just using the Roth-Hurwitz. And again, the best way to do this is to get in and try it. It's no good just talking about it or watching the video. You should go through and do the calculation and check these numbers yourself. So as you can see, as we go down the column now, because this is with the Roth-Hurwitz, we use the first column to tell us about stability. So you'll see that we've got 1 to a positive value, if you like, to a negative value, to a negative value, to a negative value. So there is one sign change in the first row as we go from row 1 to row 2. The sign has 1 right half plane pole and 2 left half plane poles. Consequently, the system is unstable. So as I say, once you do your calculations, check, double check, but then make sure all you're going to do is go through and see if there's any sign changes here, and then interpret them to see if it's stable or unstable. So that's the analog processes, looking at continuous systems. What about the digital systems? Well, again, we have stability in digital systems as well. Now, a very distinct difference between analog feedback systems and digital feedback systems is the effect that the sampling rate has on the transient response in digital systems. Changes in the sampling rate not only changes the natural response from overdamped to underdamped, but can also force a stable system to display instability. The following discussion focuses upon the digital systems from 2 perspectives: the digital system stability via the Z-plane and the digital system stability via the S-plane. Indeed, we will discover the Roth-Hurwitz criterion can be only used if the systems analysis and design is on the S-plane. All right, so digital system stability via the Z-plane when we're talking about digital systems. In the S-plane, the region of stability is the left half plane. Consider a transfer function g of s transformed into a sample data transfer function, in other words, a digital system, g of z. The region of stability on the Z-plane is evaluated by considering this little notation. So z equals e to the negative ts. If we let s equal alpha plus j omega, substitute that in, and then we'll see that we end up with this expression, which we can write in mathematics carefully. You can write it in either form, they're equivalent forms. Now, each S-plane region can be mapped into a Z region, like so. Again, remember this is mathematical principles, don't get too concerned with it. A digital system is stable if all the poles on the closed loop transfer function T of Z are inside the unit circle. Unstable if any pole is outside the unit circuit and or there are poles of multiplicity greater than 1 on the unit circuit. Marginally stable if the poles of multiplicity equal 1, in other words, they're on the unit circle and all other poles are inside the unit circuit. So really, we're going to concentrate when we talk about the Z-plane and looking at stability. It's whether or not they're inside, outside, or on that particular little circle there. Okay, so as always, that's an example. Consider the block diagram. So here we have, again, it's a unity feedback system. Keep that in mind as well. We're looking at a digital system. The determinant of the system is stable for k equals 20 and k equals 100 with a sampling interval of t equals 0.1 seconds. Now remember, sampling interval can be sampling rate, sampling time, sampling interval of 0.1 seconds. The closed loop transfer function for this digital system is equal to that, where a equals 27. Now this is a common occurrence in digital control systems, namely that you have a transfer function in cascade with a 0 order hold. So here's our little transfer function, and that's a 0 order hold. So when we put them together, we can generate the general solution for this type of problem by moving the s of the denominator over to here and then take our Z transform. So, okay, so this now G1 of S, let's concentrate on that for a moment. So G1 of S divided by S is taking our original transfer function K, A, S into S plus A, and again dividing by S will give us the S squared on the denominator. We can expand that out by partial fractions, okay, just the normal process. We've taken the K outside because it's just a constant. I need to fiddle with it, so take it out the front like I've done here. Then you go through, do your partial fraction expansion. Then you've got to take your Z transforms, just look at the Z tables, and then here the rest of this is just algebra to get a common denominator as we work our way through, so all the way down to here. And then once you've done that, you can see that you can plug this back in again. And again, it looks complicated, but just follow the mathematics, and then ultimately you can simplify very, very quickly once we know what our sampling time is or a sampling interval is. And of course, our value of A is 27. So therefore, very, very quickly, we can get down to our transfer function equals this. Now, that's great, but remember, we've got a unity feedback transfer function. So our closed loop transfer function now takes into account, as you can see, that'll be times 1 here for our G of Z, H of Z. And again, bingo, bit of algebra. But finally, we'll see that we now have our G of Z. So the question was, is the system stable for particular K values? Now you can see you've got a K value here, a K value there, a K value there from our analysis. So now what we can do is that for K equals 20, we're going to concentrate on our characteristic equation, which is always the denominator. So the denominator, and we're going to equate that to 0. So when we do that, we can see that when K equals 20, we have the roots of the equation are Z equals 0.1204 plus or minus J 0.7812. So as a result, the system is stable for K equals 0 as the poles are inside the unit circle. Okay, see how those values are all less than 1. Now for K equals 100, exactly the same thing. We take our characteristic equation, equate it to 0, and then of course we're going to substitute in our K value. So here we have all negative for our roots, Z equals negative 0.5841 and Z equals negative 4.8888. As a result, the system is unstable as the unit of the poles are outside the unit circle. All right, so big problems there. All right, the effective sampling rate on the range of stability. As indicated earlier, a very distinctive difference between analog control systems, feedback systems in particular, and digital feedback systems is the effect the sampling rate has on the transient response. So much so that changes in sampling rate not only changes the nature of the response from overdamped to undamped, but can also force a stable system to display instability. So let's have a look at this example. Determine the range of sampling interval T that will make the system stable and the range that will make it unstable. Note that all parameters are constant except for the sampling interval T. So again, we've got this unity feedback system. Keep that in mind, it is a feedback system. All right, since we're dealing with the unity feedback, H of S, so this H of S function goes around here, and the Z transform, the closed loop function or system TZ, is defined from the figure as being, as you see, it's just our typical feedback system, where this is going to be GZ divided by 1 plus G of Z. Now from the figure, we can see that these are cascaded together, so that's just our hold, our 0 hold. So again, just like we've done beforehand, we can rewrite this. We can take that S over to that side and then concentrate on that. We take the Z transform. So again, just follow the mathematics through. And once we do that, we're going to concentrate on the second term. We already got this term, we're going to come back and substitute. So just basically, we're going to concentrate on this term here now and basically simplify it. And then we're going to plug it back in again. Now, as soon as you see that, oh, it's a partial fraction we're about to generate. So you need to go through and make sure that, we've got a proper fraction, which we do have. From our definition, we know that the numerator power is lower than the denominator power. So that's great. So we do our partial fraction process. Then we've got to, so we've got this in partial fraction form, but then we've got to go find our values of A and B. We do that, and then ultimately we see that we've got that in its correct form, so we can substitute that back in and simplify. Do our Laplace transform. Okay, plug it back into our original because that's ultimately what we're trying to find. We're trying to find the G of Z. So then the rest of this process is just find common denominator. We put it back in because ultimately we want to find T of Z. Again, a lot of mathematics, but just follow the mathematics through. Again, you'll find that here we have our overall T of Z, our control function. So yes, a lot of mathematics, but the reality is that once we start to analyze that, we can see that the pole is at 11e to the negative t minus 10, considering the unit circle. So therefore then we can equate that to 1, because that's our unit circle. So as you can see, the time interval t equals 0, and at negative 1, remember that's where the other pole could be, because we're talking about unity circles, it can only be 1 or negative 1. So therefore then it equals 0.2006 seconds. Monotonically, don't be too concerned, it's some mathematical terminology. I note that the monotonically decreasing function is one that decreases as t increases for all real values of t. So as I say, just be conscious of the numbers, but mathematically that's how we go about describing it. So consequently, the pole of t of z will always be inside the unit circuit, and the system will be stable if the sampling time is between 0 and 0.2 seconds. I've just dropped a couple of others that are too small. Also, for the sampling time of between 0 and 0.2 seconds in terms of the frequency, where the frequency is 1 over t, then the system will be stable provided that the sampling frequency is 1 over 0.2, which is about 5 Hertz or greater. Now, exploring this example where all the parameters are constant except for the sampling interval t, our analysis has shown that the varying sample interval t will lead the system through regions of stability and instability as though we are varying the forward path gain k. Digital system stability via the S-plane. Now, in continuous control systems, the determination of stability is dependent upon our ability to determine whether the roots of the denominator of the closed loop transfer function are in the stable region of the S-plane. Now, when analyzing higher order systems, the analysis is complicated as the closed loop transfer function denominates in the polynomial form and not in a factorized form. So the same problem arises for closed loop sample data or basically discrete time or digital transfer functions. The tabular analysis techniques exist for determining stability, such as the Roth-Hurwitz method for both higher order continuous systems and sample data systems or digital systems. These other techniques are beyond the scope of this introduction unit and not covered here. So we're just going to concentrate on the Roth-Hurwitz method in reality. So in using the Z-plane, we have identified that sample systems are stable if their poles are inside the unit circle. Unfortunately, this criterion for stability precludes the use of the Roth-Hurwitz method, which detect roots in the right half plane rather than outside the unit circle. However, we can accommodate the use of the Roth-Hurwitz method in conjunction with the S-plane to determine the stability of a sample system, even so. This is achieved by using bilinear transformations, and by analyzing and designing on the S-plane and then using these transformations, we can convert the results to a digital system that contains the same properties. So basically what we're doing is it's just transferring across, enabling us to operate within that parameters that we can use the Roth-Hurwitz, and therefore then apply a technique that's already used for the analog system. So what you do here is you consider that z equals e to the ts and its inverse. So that's going to be the inverse of an exponential function is a log function. So s equals 1 over t to log z. Now as the direct transformation between z and s, that will enable us to basically do that by linear transformation. Now further, if we have g of z and substitute e to the ts, then we can obtain g, the transfer function, e to the ts as a result of converting to the s-plane. Now similarly, if we have g of s and substitute s equal 1 on t to log z, then obviously we can obtain g as a function of 1 on d log z, and we can convert to the z-plane. Now both transformations, so you can use either one, both transformations can be analysed through a z-transform, but this can become complicated. So ideally we are seeking a simple process for bilinear transformations, that is, where bilinear means in both directions. Go from the s-plane to the z-plane, or from the z-plane to the s-plane, which will result in a linear forms through direct substitution without using complicated z-transforms. This can be enacted to yield linear variables s and z by using a bilinear transformation. So this is what we're going to do here. So these little rules we can use to help us transform between systems. So different values of A, B, and C and D have been derived for specific applications and result in various degrees of accuracy when comparing properties of continuous and sample functions. This type of analysis is explored in the next section. As a consequence, it will be demonstrate how a particular choice of coefficients will take points on the unit circuit and map them onto points on the JW axis or the imaginary axis, J omega axis. Points outside the unit circle will be mapped into the right half plane, and points inside the unit circle will be mapped into the left half plane. Consequently, we will be able to process a simple transformation from Z plane to S plane and derive stability information about a digital system by working in the S plane. It's important to keep in mind that the transformations are approximations and not exact. Only the property for which they are designed can be relied upon. For the stability transformations discussed above, we cannot expect the resulting G of S to have the same transfer response of G of Z, as we are working with only an approximation to establish the transformation. However, let's explore another transformation that will retain that property. So let's consider the situation where a bilinear transformation maps J omega, the imaginary axis points on the S plane, to the unit circle points on the Z plane. Further to this, the transformation also maps right half plane points on the S plane to points outside the unit circle on the Z plane. And finally, the transformation maps left half points on the S plane to points inside the unit circle on the Z plane. This means we're able to transform the denominator of the pulse transfer function d of Z to the denominator of a continuous transfer function d of S, and use the Roth-Hurwitz criterion to determine system stability. The bilinear transformation achieves this is of this particular form. Now, as you can see, this is much simpler, isn't it? So this can be demonstrated as follows. If we let S equal alpha plus J omega and make the transformation from the S to the Z plane, or S to the Z variables, then you plug all that in, and then you can determine the magnitude. So therefore, then when you do that, if it's less than 1, then it must be inside the unit circle. If it's greater than 1, it must be outside the unit circle. And then ultimately, if it equals 1, then it must be on the unit circle. The following example provides insights to how the stability of a sample system can be determined using the bilinear transformation and the Roth-Hurwitz criterion. So in other words, we can use the Roth-Hurwitz like we've done with the analog systems, but we must do this bilinear transformation. And the bilinear transformation you choose is this simpler form that we've just been talking about. So again, as I say, if you find the mathematical gobbledygook, don't worry. Go and look at the worked examples. Make sure you follow and go through, the worked example, work through it again, and make sure you understand the processes. So here we have Tz equals Nz, the numerator, divided by the denominator, d, where the denominator equals z cubed minus z squared minus 0.2z plus 0.1. Use the Roth-Hurwitz criterion to find the number of z-plane poles of T of z inside, outside, and on the unit circle. Is the system stable? All right, so we don't really know what Nz is, and we don't really need to, because we're just going to concentrate on the denominator, which we know is our characteristic equation. Set that to 0, fantastic. Then we're going to perform this by linear transformation using that little transformation function z equals s plus 1 divided by s minus 2. So what we're going to do is plug it in there and equate it to 0, as you can see. So wherever we see a z, go and put an s plus 1 divided by an s minus 1. Okay, then you got to multiply them out, establish a common denominator. Good thing is you can multiply both sides by that, and that's it's 0. So now you've got to multiply that out. And as you can see, if you collect all our terms, after all that work, it turns out not to be a terrible function anyway. So our characteristic equation for this digital system is s cubed minus 19s squared minus 45s minus 17 equals 0. So then we go about, just like we've done beforehand, using the Roth-Hurwitz that we did for the analog system, but now using it for the digital system. So we use that bilinear transformation. So again, like we did beforehand, s cubed, s squared, s1, and s0. Now, if we look at this, we've got a coefficient of 1, and we take the alternative value, negative 45. Then we write down the s squared, which is negative 19, take the alternative, which is minus alternative term, minus 17. Go through like we did beforehand, using the pivot point of negative 19 in this case, generate our values, go through, and as you can see, we end up with a Roth-Hurwitz table that looks like this. Now, as we go through, we can see we've got a sign change as we go from S3 row to the S2 row, and then everything stays the same. So there's only one sign change in the first row, row 1 to row 2, 1 positive to negative 19, which means that the system has 1 right half plane and 2 left half plane poles. So therefore, T of Z has 1 pole outside the unit circle and no poles in the unit circle, and 2 poles inside the unit circle. So the system has 1 pole outside the unit circle. As soon as that occurs, it's unstable. But as you can see, the key thing is that just like the analog system, you can use the Roth-Hurwitz table and generate it and then analyze it by looking at that first column, but you must go through and do that bilinear transformation. All right, good. So, as I say, with all the mathematics, if you find it gobbledygooky and that type of thing, get in and look at the worked example, follow line by line, follow the process of the advice that's been given, and also make sure you're working through the tutorial problems, and ultimately if there's an assignment question, things like that. Do the mathematics, follow through the mathematics. That's the key feature and facet that best advice I can give you.